Hello everybody, welcome back. Today we're going to start talking about Fibonacci numbers and algorithms to compute them. In particular, in this lecture, we're just going to introduce the sequence of Fibonacci numbers and talk a little bit about their properties. So, to begin with, the Fibonacci numbers is a fairly classically studied sequence of natural numbers. The 0th element of the sequence is 0, the first element is 1, and from there on, each element is the sum of the previous two. So 0 and 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and then the sequence continues 8, 13, 21, 34, and so on. So it's a nice sequence of numbers defined by some pretty simple recursive rule, and it's interesting for a number of reasons. It has some interesting number theoretic properties. But originally, this sequence was developed by an Italian mathematician as a mathematical model. And it's a little bit weird. You might try and wonder what sorts of things this could be a model for. Well, it turns out that originally this was used as sort of a mathematical model for rabbit populations. There was some idea that if you had a pair of rabbits, it would take them one generation to mature, and every generation thereafter they'd produce a pair of offspring. And if you work out what this means, then you find out the Fibonacci numbers tell you how many pairs of rabbits you have after n generations. Now, because rabbits are known for reproducing rather quickly, you might assume that this sequence therefore grows quickly. And in fact, it does. It's not hard to show that the nth Fibonacci number is at least 2 to the n over 2 for all n at least 6. And the proof can be made by induction. You prove this directly for n 6 or 7 just by computing the numbers and showing that they're big enough. And after that point, f of n is the sum of fn minus 1 and fn minus 2. By the inductive hypothesis, you bound that below and do a little bit of arithmetic, and it's bounded below by 2 to the n over 2. So that completes the proof. In fact, with a little bit more work, you can actually get a formula for the nth Fibonacci number as roughly 1 square root of 5 over 2 to the n. These things grow exponentially quickly. And to sort of drive that home a little bit more, we can look at some examples. The 20th Fibonacci number is 6,765. The 50th Fibonacci number is approximately 12 billion. The 100th Fibonacci number is much, much bigger than that. And the 500th Fibonacci number is this monster with something like 100 digits to it. So these numbers do get rather large quite quickly. So the problem that we're going to be looking into for the next couple of lectures is how do you compute Fibonacci numbers. So if you want to use them to model rabbit populations or because of some number theoretic interest, we'd like an algorithm that as input takes a non-negative integer n and returns the nth Fibonacci number. And we're going to talk about how you go about doing this. So come back next lecture and we'll talk about that.